Welcome to Systems Engineering for Engineering Management 4010. This is Daniel Paz, and I'm going to cover the second week in this video. First week we talk about why we need system engineering, and in this second video we're going to start breaking it down how we go about it. We're going to talk about key concepts that are required to start breaking apart the process of doing system engineering. So, 4 parts of this lecture. Some of the concepts that I will be explaining in this video were covered in the first week, and I focus much more on process. So what is system engineering process, SEP, and why they are important. There are specific processes that we need to conduct to do system engineering. The other part is the system engineering life cycle. So we combine the life cycle that we quickly talk about in week 1 and go deeper to understand how it's integrated as part of the process. We then talk about a key process in system engineering called System Decomposition and Integration. So we put it apart and then put it back in. We put it apart in this week, and we're going to put it back in the next lecture. And trade-off analysis of system engineering. In other words, how we know what is the best solution. It's impossible to have them all converted into one place. It's impossible to get the perfect solution. We know as engineers what we try to do is improve our outcomes. In this particular week, I'm going to cover what key parts of that analysis are important in system engineering. So let's start talking about the first part, what is the key components of processes. And one out of these lessons, the second week, that you learned about understanding the system engineering process, explaining the balance that you have in system engineering, how somehow you have to balance different interests, and how you break down key concepts. There are extra material in the lecture notes, and it's important to keep in mind that the information I provide in this lecture will be complemented with individual and group exercises that we'll be doing during the subject. So, the system engineering process, why is it important? The system engineering process is a structured, iterative approach used to manage the design, integration, and operation of complex systems. It ensures that all technical and management aspects are addressed effectively and that stakeholder requirements are met. We follow a process to make sure that when we apply system engineering, simplifying a very complex problem so we understand complexity. Remember, we cannot dissolve complexity. Complexity is always going to be there. It's always complex to take a rocket into space. What we do is a process that helps us doing that better. Now, system engineering process, it is related to the life cycle that we talk about. A project has a life cycle. System engineering process has also the process of having a life cycle, a step that are following. A little bit of a difference is that it doesn't have to go back to the start like a normal process. When you finish a process, you pretty much start with the next process. In this one, doesn't happen like that. We have a key steps, 7 steps that we follow in system engineering. The first one is concept development, so identifying what is the need to do system engineering, why you're doing system engineering, and if you are looking at solving a problem or you're actually creating a new system. Requirements definitions, why we need to solve it. No, we talked last week about the 737 MAX aircraft accidents. 2 aircraft fall off the sky and many people died. What are the key components in solving that problem? Why we need to solve it, and what are the key solution we are proposing? And in that case, of course, was able to have the 737 MAX again in the air, which is after a year and a half was able to be put back in the air. System design and development. So we want to, after we have the requirement definition, want to start talking about the system design and development. How we're going to go about the system. Remember, the system could be a problem. The system could be a new product. The system could be a new software. There could be many things. And then we're going to do the integration and testing. You need to integrate it with the existing system. The 737 MAX aircraft needs to fly with other aircrafts that are in the airspace. The same, if you put in a new transport system, it needs to be integrated with the existing transport system of a city. Or if you're going to put a new logistic approach in a port, it needs to be integrated to the existing logistic that exists in the specific port. Now then we have implementation and development. What are those keys transitioning from design to the real world? What are those key components that will allow us to develop that integration? And it becomes very important that in that step 5, what are the connection between our stakeholders that will help us doing that integration and the design that we had developed and implemented. Operations and maintenance and the commissioning and disposal. Goes back now connected to the life cycle, but we break out the system into the process that the system engineering will have to be able to conduct a project. Let's now look at in a much more complex approach when you have very difficult systems that have multiple functions, that have multiple components, and you need to be able to follow a process to do system engineering. So in the system engineering process diagram, the one that I have on the screen, and please remember many of these diagrams are coming from the Bible or a key aspect of system engineering literature, which is the handbook provided by NASA. The latest version is 2020. Now, there's in the material other books that you can consult, and there are specific ones for some sectors of Australia, but a system engineering that you use for rockets, which is the case of NASA, no? Aerospace engineering, is likely to be suitable for many other problems or other engineering problems that you have. However, it's going to be complex because it's made up to deal with very complex problems. Not taking a rocket to space is a very complex aeronautical, thermochemical process that requires a lot of different processes. But even if your problem is not as big, you're always going to be able to recognize these processes that exist in the whole system engineering process. You're going to be able to see a design process, a technical management process, and product realization process. So there is always these three, the ones that I have in the middle in red, 3 bunch of processes that will allow you to guide design, management, and realization of the project. So you have to think from designing into managing the production into be able to put it into execution. And each of those processes will have inputs and outputs. The input for design will be the requirements. The output will be how to do them. The input for realization will be the product production, and of course the realized product will be at the end the outcome of the whole process. So we have a big system engineering, and to be able to analyze what's happening inside those very complex systems, we're going to break them into these 3 big groups: design, process, and management. Later on, in a couple of weeks, when we talk about stakeholder management, you will see how the system also have parts that are moving between the systems, and this is not completely linear. There are other important relationships between the different systems. So from week 1, remember, we always have in the basic, a typical characteristic of a system is that you have a purpose for that system. There is function that each part of the system has, and the performance of the system is affected by how the parts are arranged. And that concept of stability becomes almost like a benchmark for all systems. You define stability. Stability is being able to fly at 24,000 kilometers per hour like a rocket. Doesn't matter how you define it, but you want it to be stable based on the conditions that you give it. Taking in consideration of all these characteristics of a system and the system life cycle, I want you to start thinking that every time I do a process for design, for management, or for deployment, I have a mini life cycle. I go back and develop those concepts that give me the life cycle of very high level thinking, designing, deployment, reviewing. And you can see here in this diagram At the top, I have the overall project lifecycle in the horizontal axle, and in the vertical one going up and down, I have the individual mini life cycles of each of those processes. So it's like having, every time you break in a project, even if you are in the design phase, within the design phase there will be a cycle, a life cycle. You will start with the design of the design, and you will be getting the output of the design to go to the next cycle. But that is a cycle, and there will be feedback loops and the ability to provide an input and an output to the other parts of the design. In a project, this becomes very important because something that we talk about in part one. I'm trying to identify what are those key leverage points, what are the key things that I can move and tune, and with the ratio between resources and output is larger. There's some aspect that I can change that causes significant changes to the system. We talked in lecture one about a plane. If you change the hinges, it's a significant change compared if you change the kitchen that heats up the food for the passengers. So those, I want to identify what are those key things that affect the system the most. If I break it out into life cycles within the different processes and their life cycles, I'm able to start identifying what are those key points that give me the ability to better understand where I can make improvements in my designs, in my construction or my deployment to do a better project. Remember, and I go back here because we tend to think engineering systems is about new products. No, it's always about functions that are made by parts, and it could be a problem that exists. Remember the 737 MAX problem, or a new rocket that we're going to put on space, or a new transport system that we're going to put in a city. So it could be a new or an existing, it could be a design problem or a identification of a problem. They still are the components of a life cycle into system engineering. Taking this into account, most processes in system engineering, if not all, will require decomposing. I showed this photo in the first week. You need to put it apart. It is too hard. No, when you ask, there is a famous say here in Australia, what is the best way to eat an elephant? And the answer is break it out into parts that you can chew one at a time. So this is basically what we do in system engineering. Now, how you break that into parts? Do you need to put apart the 737 MAX to be able to do that? Or there are other options to be able to do that? I'm going to show you what are the standards to be able to break apart a big problem that you got, that you're going to use system engineering to break it. We know you have life cycle. You know, at a high level, you think about a problem, you design it, you implement it, and you review it. At a more detailed level, you need to break it into parts and be able to break down that design, break down that implementation, break it down to do those specific parts. So decomposing is, system decomposition is the process of breaking down a complex system into smaller, manageable subsystems while maintaining overall functionality. Why we do it? Simplify complex systems, enhance design and development, improve troubleshooting. When you have a problem that is not working or something is happening, if you break it down, you might be able to do it. Software engineers are very good at this. They would put error handling so they can see where the process, where the script is stopping. Enhance parallel development and reduces risk. Something we talk in week one. One of the purposes of having system engineering is to have less risk. Now, what is the typical example? Decomposing an electric car, like I showed in the previous slide. Yes, you can decompose it using every single part and put it apart, which was one approach, or you can do it like they did in the providing solution for the 737 MAX, something that we will do an activity in class, which was much more about understanding the functions and where were the functions that fail in that particular system. So, how we do it? 7 steps. These steps are taken from the Handbook of NASA. You can see more of those in different approaches, but this is the basic steps that you're going to follow for decomposing. The first one is identify the system purpose. The second one is determine the main functions. You need to go from those that are the very important to the less important. So imagine on a car, the one that move it, the one that maintain it together, the one that provides suspension, propulsion, fuel, and all those things. Then you go individually on those main components into subsystems, and then establish relationship between those subsystems. So, there's a relationship between the chassis and the suspension. There's the engine, a relationship with the transmission, and so on. Of course, set boundaries and interfaces. There's a moment in where the function needs to stop, and you are able to create those boundaries, apply a hierarchical structure, and refine and optimize. What's the best way to learn decomposing? Is to do it. So try to decompose something. In the first week, we try to decompose how the food that you ate that day got to you. Now, try to decompose a system that is in front of you, your computer. How that computer is able to provide you a message. Think for a second and see how we do it. We will do an activity during the class in where we will decompose very complex systems and develop some of these strategies. Now, not everything is very rose in system engineering. We bring system engineering because the problems are bigger than us. It's not just something that I can put in a calculator or ask ChatGPT to solve it. It's too big for us to solve. So we have to break apart the complexity. We do not dissolve complexity in system engineering. We manage complexity. But we have to manage it within some boundaries, some parameters, where you have to put your energy in a world of limited resources, because when you go into a project, engineer project, no one will give you unlimited resources. They don't exist. You always have limitation in time, you have limitations in financial resources, in materials, in ability of people, and it's the same with software. You have a limited capacity on your processor, the size of the screen. You're gonna work in limitations. So how to work with those trade-offs? Because by constraining resources in one end, by expanding in others, but where will be better to do it? And that's when we analyze trade-off. And in trade-off, a key process in resource trade-off is a process in where systems engineering design or create different choices. And those choices normally are compare cost, compare performance, analyze risk, and what is the feasibility of being able to implement that specific solution. There might be a fantastic solution for your software, but it might have some difficulties in being able to be taken by stakeholders or accepted by stakeholders. So that becomes very important. What are the trade-offs? So there are trade-off analysis, and in this tutorial, in preparation for assignment 1, your portfolio, but also assignment 2, you need to have in your mind what are those kind of things, the trade-off I have. I'm gaining something but losing something else, and that's always happens when I'm doing system engineering. What are those trade-offs? The key trade-offs are cost and performance, weight and strength, reliability and innovation, automation and human control, speed and accuracy. They are very high level. Of course, for specific areas, they might be more or different, but this is the ones that, based on the handbook by NASA, you understand where you are doing trade-off. I'm gonna repeat them. Cost and performance, weight and strength, reliability and innovation, automation and human control, speed and accuracy. Yes, you reduce cost by giving ChatGPT tasks to do, but what is the trade-off there? More processing, intellectual processing by ChatGPT. What happens with the ability to have a human perspective? What are the trade-offs in your particular project, either software or autonomous vehicle or whatever you are analyzing? Now, it's important to do trade-off, because in a real world, when we're working for someone as an engineer, they will require you to do it. They will help you balance competing factors such as cost, performance, safety, and sustainability, ensures optimal decision making or improve the decision making. Sometimes you're going to be the decision making, identifies potential risks and weaknesses, which is fundamental. And some stakeholders will care a lot about accuracy or safety instead of speed, for example. They want the data produced to ChatGPT to be very accurate, so they're willing to wait for the processing to be taking longer. And now I'm giving you a little bit of software development ideas. So that becomes very important, that you understand that by doing something, you have a trade-off in doing something. In a software that I'm working at the moment, I have to work with either DeepSeek, the Hong Kong-based open source AI generator, or ChatGPT. ChatGPT is more expensive, but it can deal with more languages than DeepSeek. DeepSeek can only deal with 2 languages. So that's a trade-off. One is more expensive, more languages, the other one has less language. So what will be in that part? Breaking it to system, using system engineering, and understand I'm using trade-offs for this particular. Now, where to put the effort? And this diagram, we're going to repeat it in multiple lectures, and we're going to play with it in class. But this is very important because this diagram shows how lifecycle costs are committed early in the system development process, even though to actual expenditure occur later. So it becomes fundamental that early in the system is where you actually going to have the impacts later in the process. And if you look at this diagram, when you change designs and concepts and so on, the impact is exponential. If you change something at the end, it's going to cost you much more than if you change it in the paper when designing. And it looks obvious, but it's important to keep in mind. So you know where you have to put the energy in the different parts of the life cycle of the project. And that's part of system engineering. A good system engineer recognizes where is the energy required in those moments, because there's limited energy. So if you're doing design and you know if you change that part of the design later in the stage, it's going to be more expensive than if you change it now. So you put the energy to try to improve your outcome in that moment, that other things that you can change and not going to be that expensive. I'll give you an example. The type of propulsion of a plane. You're going to use propellers or turbines. Changing that in the design is easy, but later on will be expensive. Now, the color of the plane may be something that will have an impact. It will be expensive if you change the color at the end, but less impact in implementation. Because the connection between the parts is reduced. But which one of those parts you need to do? And that's why you do trade-offs. You understand in what moment you need to do better for the specific idea. Very good. Going back, feedback loop, leverage point. 2 concepts I'm going to continue repeating in every subject that I want you to always remember. Feedback loop, you always get something, feedback out of what you do in system engineering. When I put things apart, I get feedback. When I put them together to make them work together, I get feedback. And leverage point, I am trying to identify what matters. In big problems, there's too many parts moving, but what are those parts that if I change, I adjust, I tune, will create the biggest impact on the whole system. And that is 2 concepts that we do in trade-off, we do in life cycle, and in the processes that we explain in this lecture. Summary. Key topic cover. Please go back to your readings in the lecture. Remember, we have conversation during the tutorial and the lecture this week. What is system engineering process? The system engineering life cycle, you have to have memorized pretty much by now. System decomposition and integration, and trade-off analysis. Big summary is I do everything if a life cycle and divide it in processes that have their own life cycles, and I understand as a system engineer that there is trade-off. Always I work in a contained environment in where resources are restricted, and it's important for me to recognize that. All right. Takeaways, remember for this week, early decision making is more significant than in the later stages. A structured SE cycle reduces system failure. Proper decomposition and integration ensures system efficiency, and trade-off is part of all system engineering analysis. Next week, we're going to start talking about requirements. How you do the first part of identifying requirements. If you want to see deep details on the graphs that I show, go to the Handbook by NASA. Here's the link, and we will discuss further all these topics in our lecture.